Alright, so very good evening to all of you. Now we would be talking about the 27 December 2019 section B organic chemistry questions, right? Section B. So I had got a lot of requests because not many educators have discussed the section B solutions, and the section B, to be very honest, was quite conceptual and was quite different than the kind of questions that you usually see in the CSR examination, right? So let's discuss those questions. One more thing, that I've already discussed the spectroscopy questions that were asked in the 27 December examination, the organic spectroscopy questions, both 2 markers and 4 markers. So I won't be discussing them in this particular video. All right. So this is the first question. This is from your general organic chemistry, and basically this you only have to determine the stability of the carbocation. So you are doing basically your acid hydrolysis, or you're just adding the acid, which is basically will act as a electrophile, and you have to predict among the 4 options which is correct, right? So first, you're basically in D3O plus, you will have D plus, and there will be D2O, right? This is one way to write it. So basically this will act as an electrophile. Now the only thing that you need to determine over here is what will the stability of the carbocations, right? So let's draw what kind of carbocations can we have. So let's say the deuterium attaches at this position, or at this, or at this, right? So I can write 1, 2, 3, 4. So there are 4 positions where the deuterium can attach. So let's quickly do that and see where all the carbocation will be generated. So if the deuterium attaches over here, the carbocation is generated over here. So this is one. This is one. The second one that we can have is where the deuterium attaches at the position number 2. So we'll have a benzylic carbocation that will be generated, right? Then in the third case, we can have a carbocation that will be basically generated over here if the deuterium attaches at the terminal position. And one more carbocation we can have is this one, where basically the double bond would be here, and then we would have a primary carbocation that will be generated, right? So obviously the primary carbocation is the most unstable in this case, so you can cancel this out. In among this also, this carbocation is also not stable. Now a lot of you might be confused among this option, let's say the second option, and let's say this is the fourth option, right? So you might have some confusion over here. So this over here is a more stable carbocation, the 4 number, okay, because this bond can resonate over here, and then this carbocation can be generated over here. So there will be a long conjugation in this particular case, because of which this carbocation will be stable. So you can see it so over here the deuterium has attached at the terminal position. So among the 4 options that are given, you can see the deuterium is there in the 4th option at the terminal position. So this is the correct answer, right? Let's move forward. So the next question is quite simple. It is from Birch Reduction, and this is phenanthrene molecule given to us, right? Phenanthrene, and in phenanthrene, you are doing Birch reduction, right? So you have to see, whenever these kind of questions have are come up from Birch reduction, you just have to see where is the least, you can say, when the reduction takes place, where will the least amount of aromaticity lost. Okay, so if in the first option you see, we get 2 aromatic rings over here, and then the third ring loses its aromaticity. In the second option, there are 2 aromatic rings, and both of them are basically not directly you can say attached to each other. So in this case there is some kind of annihilation effect that is taking place. In this case there is no annihilation effect, so this over here takes priority, the second option, right? In the third option, you can see all the 3 rings have lost aromaticity. In the fourth option also, all the 3 rings have lost the aromaticity. So this is quite simple over here, that the correct answer would be option number 2. All right. Now the next question is basically it is from medicinal chemistry portion, and I think maybe the examiner did not have that time, so he just put up one question, which is basically a question which is directly based on mugging up, and it asks the anti-HIV drug. So the anti-HIV drug over here is zidovudine. Okay, it's a very expensive drug used for it's an antiviral, basically an anti-HIV agent, and it has a azide structure. It has an azide moiety present in this molecule. All right. Okay, this is a very interesting question, and it says that the correct order of elution of amino acids 1 to 4 with a buffer of pH 4 from a column containing anion exchange resin. Okay, so anion exchange resin is basically a quaternary ammonium salt. Okay, quaternary ammonium ion, which is basically stabilized by OH minus. So this is basically your anion exchange resins. Okay, so if this is your anion exchange resin, then what that means is that the more polar the molecule, okay, the more polar the molecule, or you can say the more acidic the molecule, the higher the chances that it will bind to this NH4. Okay, see, because what has been mentioned, the pH is the buffer is at pH 4. That means uh, what would happen is the more polar, like it will, this over here will exist in the form of COO minus. Okay, this over here will exist in the form of COO minus, right? Or just think about it this way, that the more polar amino acid, the more polar the amino acid, the more it will be retained. Okay, because the polar amino acids will basically bind to this buffer, right? This is quaternary buffer, so you can think of it in this way, that it is deficient, you can say, or it is positively charged. So the polar over here, the polar amino acids will basically bind to this, so they will strongly bind, so they will elute at the end. Okay, so I can write over here, the polar amino acids, the polar amino acids will elute, okay, or will come out. Elute basically means will come out of the resin at last, will elute at last. Okay, so that means among the four options, see, this is a histidine molecule, so you just needed to know which molecules are which amino acids are polar and which are non-polar. So among the four options, this is a neutral, this is leucine. Okay, the second option over here, this is leucine, so this is basically a neutral, you can say a neutral amino acid. Okay, then this over here is cysteine. Okay, cysteine is a bit polar, and this one over here is our your aspartic acid, right? This one over here is aspartic acid, which is very polar in nature, right? So the aspartic acid is the most polar, and your cysteine is a little less polar. Your leucine is neutral, and over here this is histidine. This histidine is basically you can say non-polar. Okay, histidine is a non-polar amino acid, right? So among the four options, if you see, histidine will elute first, because it will not bind to the quaternary or anion exchange resin at all. Then your leucine will elute, then followed by cysteine, and then your aspartic acid. So one first this will elute, then 1 2 3 4 basically. So the correct answer would be option number 1. Okay, this was a good question, and this is not these kind of questions have not been asked before. Maybe a long time back, but not anytime recently, right? So this is again a different question, a easy one, but these kind of questions again have not been very frequently asked. And the question says that the correct statement about the product formed when D-glucose is reacted with dilute HNO3. Okay, so when glucose is reacted with dilute HNO3, what it forms is carbox. It basically oxidizes the CHO and the CH2O group. Okay, so we have a CHO group in glucose, and then we have basically, and then we have a CH2OH group, right? So this is basically the structure of glucose, and what it says, we are adding dilute HNO3, right? So when you add dilute HNO3 to this, and now dilute HNO3 is a strong oxidizing agent, right? So what it will do is basically it will convert your aldehyde into carboxylic acid, and it will also convert your alcohol also into the carboxylic acid, right? So it will convert both of them into the carboxylic acid, right? Now the question says that which of the following statements is correct, right? So this third option says that the product shows a signal at 12 to 13 ppm in the proton NMR spectrum. Okay, the product shows a signal at 12 to 13 ppm in the proton NMR spectrum. So this 12 to 13 ppm belongs to the acidic proton of the carboxylic acid. So this option is absolutely correct. The second option says that we will see IR stretching around 1740, which is not correct, because for carboxylic you generally see around 1690 or around 1680 or 1700 centimeter inverse. The product is optically inactive, which is not correct, because over here we'll have different kinds of chiral centers which will make it optically active, because those will not be changed at all. Okay, then the last option says that the product gives a brick red precipitate upon treatment with Fehling solution, which is absolutely incorrect, because there has to be a presence of aldehyde to for it to give Fehling test, right? So there's no aldehyde present, because it has been oxidized to a carboxylic acid. So this is also incorrect. Okay, I'm not sure about this, whether it will oxidize your alcohol to carboxylic acid, but definitely the aldehyde will be oxidized to the carboxylic acid. This you can once check it out by yourself, whether it happens or not. Okay, again this is a question from your general organic chemistry, and over here it's asking the most acidic hydrocarbon among the four options. Okay, If you see, you just have to make such carbon ions. Basically, if you are being asked about the acidity, basically you have to talk about H plus donating capability. So if you are donating the H plus, whatever the conjugate base is forming, which will be a carbon ion, because if you're donating H plus, basically a carbon ion will be generated, right? For example, if I am taking out a H plus from just let me change the color. Yeah. So if I'm taking out a there's a hydrogen over here. So if I'm talking about it, talking about the hydrocarbons acidity, how acidic it is. So I'm basically talking about the H plus donating capability. So once it donates the H plus, what will happen is that a carbon ion will be generated over here, right? So basically we have to see the stability of the carbon ions. Now in the first case, if I take out this hydrogen over here, we would get a tertiary carbon ion in the first case. Okay, in the second case, which hydrogen we have this hydrogen over here, right? So this will give us a primary carbon ion, because once this hydrogen is eliminated or this is donated, we'll get a carbon ion over here, right? So this will generate a primary carbon ion. Then in the third option, again, if you see, this hydrogen will be eliminated, and again we'll get a tertiary carbon ion, right? Over here also we'll get a tertiary carbon ion. And the fourth option, you'll get a primary carbon ion over here, right? Now let's talk about, see, so these tertiary carbon ions will be very unstable, so let's talk about both the primary carbon ions. So this is one option in which we'll get a primary carbon ion, right? The first option. So let me just quickly draw these structures. um, so we have a double bond over here and a double bond over here. So this is one structure. Okay, and we'll get basically in this case, in the first option we are getting a tertiary carbon ion, so that is not what we want. In the second option we are getting a primary carbon ion, right? So in the second option, if I quickly draw, um, we have 5-membered ring, and in this 5-membered ring we have this double bond over here and then over here, and then we have a carbon ion that will be generated at this position, right? So this is one, this is second option. And if I talk about the fourth option, where again we'll get a primary carbon ion, so over here this is the structure. Okay, and so we have a double bond over here and over here and like this. Okay, now if you see, among four, and then we'll generate a carbon ion over here, right? So what can happen is this carbon ion can migrate over here. Okay, and this bond can migrate over here, but this will not turn into an aromatic ring. So there is stabilization, but not that great. Whereas if you see this option, if if this goes over here, right, this negative charge migrates over here, and we get a negative charge at this position. So convert it if I convert the molecules so that you can see it in a better fashion, we basically get an aromatic ring, right? This is an aromatic ring. So there is extra stabilization in the second option. You can see because of this because it gains the aromaticity. This ring gains the aromaticity. So that is why the correct answer over here is second option, because this will be most acidic, because the conjugate base over here is very stable. All right. All right, this is an interesting question. Again, a little different than the usual questions that are asked. So the question says that the major product formed in the following reaction is optically active because it possesses what? So you are basically doing reduction, and basically it's a keto reductase. This is a big hint given to you. So that means this you can say this carbonyl group will be reduced. Okay, and since you can see it's enzyme, it's basically uh, a natural enzyme, so they are very specific in nature, right? So let's say this OH goes above the plane and this hydrogen goes below the plane, let's assume. Okay, and then we'll have a carboxylic acid over here and a hydrogen over here. So these kinds of molecules are basically you can refer to them as cycloalkylidines. Okay, cycloalkylidines. Okay, alkylidine. Okay, cycloalkylidine. So these are the molecules, and these cycloalkylidines are basically having a chiral axis. Okay, they are having a chiral axis, so they are optically active, and they are optically active because they are having a chiral axis. So the correct answer over here is option number 2. Okay, right. So this is a very interesting question which has been asked, and it says the reaction that will show a non-zero deuterium kinetic isotope effect. Okay, so this I'll just try to explain in a bit of the detail what exactly is your deuterium kinetic isotope effect, right? So this basically tells us the ratio of Kh upon Kd. Okay, ratio of Kh upon Kd, that is the speed at which the reaction happens with respect to hydrogen and with respect to deuterium. Okay, so this is a ratio which tells us about the uh, kinetic isotopic effect, right? Now if this value is greater than 1, then we say that it has some kind of effect, and if the kh upon kd value is less than 1, then we say it does not have any effect, right? So it is asking you non-zero deuterium kinetic isotope effect. Now before we move on to that, let me just discuss what exactly do we mean by the deuterium kinetic isotopic effect, right? So generally what you observe is that since the masses of hydrogen and deuterium are very different, okay, deuterium is almost double, the frequency with which your carbon deuterium bond vibrates and the frequency with which your carbon hydrogen bond vibrate is very different, okay. Now carbon hydrogen bond is basically weaker as compared to your carbon deuterium bond, okay. This is of higher energy. Carbon hydrogen bond is of higher energy, so it is, this bond can be easily broken. The carbon hydrogen bond can be easily broken as compared to the carbon deuterium bond, which is difficult, okay. This carbon deuterium bond is difficult to break as compared to carbon hydrogen bond, right? So what happens is, if there is a reaction, if there is a certain reaction which depends on the rate, or the slow step of that reaction depends on the abstraction of the proton, then it would be different, the rates would be different, because if the slow step is abstraction of the proton, then if you have a deuterium attached, then it will be very difficult for, let's say, the base to abstract that proton, and that's why the reaction will take a lot of time. Whereas if we have carbon hydrogen bond, that will be easily abstracted, and this reaction will happen faster because of the higher energy of the carbon hydrogen bond, right? So that is why if I have kh upon kd greater than 1, then I can say that the slow step of the reaction depends on this carbon hydrogen bond or the carbon deuterium bond, okay. Whereas if kh upon kd is almost equal to 0, then I can say that it does not depend on the slow step of the reaction, or the rate of the reaction does not depend on the abstraction of the carbon hydrogen or the carbon deuterium bond, basically, right? So this is what kinetic isotopic effect tells us, and it has been practically also used a lot. All right. So now let's look at the question. So we basically have to see in which of the three options does basically the kh upon kd, it's asking non-zero, means we have to see such a reaction in which your the rate of the reaction does depend on the carbon hydrogen bond breakage, or basically the carbon hydrogen bond breakage. We have to see a reaction because it's asking non-zero deuterium kinetic isotopic effect. So we have to see a reaction where the slow step involves, or the rate of the reaction involves, the breaking of the carbon hydrogen bond, okay. Now in the first option, if you see, this is basically a tertiary alcohol and you're adding acid, so basically it will protonate the OH, and it will basically lead to a SN1 type reaction, where basically this is your leaving group, and this leaving group will basically leave and a carbocation will be generated, right? So in this particular case, the generation of the carbocation is basically the rate determining step, okay. The generation of the carbocation is the rate determining step. So you can see there is no involvement of your carbon hydrogen or carbon deuterium. Basically there is no involvement of the carbon hydrogen bond over here. So this will have a zero deuterium kinetic isotopic effect. So this will have a zero kinetic isotopic effect. So this you can cancel out, option number 1. So let's look at option number 3 over here. So 3 you can see is basically a even CV mechanism, where you are adding a base and you have a stabilizing group present. So when you add the base will abstract this proton, okay. But you have to remember this. Now you might be thinking that, okay, the base is abstracting the proton, so this is a rate determining step. But in even CV mechanism, this is not the rate determining step, okay. The abstraction of proton is not the rate determining step. The rate determining step is actually the elimination of the leaving group. So in this case, the leaving group is our OH. So elimination of the leaving group is the rate determining step, okay. So this is the rate determining step, and that is why and the abstraction of the proton is not the rate determining step. So it will not matter whether we are abstracting the carbon hydrogen bond or the carbon deuterium bond, because that is not the rate determining step. So this will also have a zero kinetic isotopic effect. So the only answer is option number B, because over here I'll just quickly tell you that if we have in this case, the rate determining step is basically the base abstracts the proton, and then the proton migrates over here and the leaving group leaves. So this is the rate determining step, and over here the abstraction of the proton is a part of the rate determining step. So if we have a deuterium over here, the rate of the reaction will be slower, and because we have a proton over here, the rate of the reaction will be faster, and that is why we will have a non-zero deuterium kinetic isotopic effect and that is why the correct answer will be only B. A very interesting question. All right, I'm basically explaining a little quicker because it's a solution video. If in case you want me to explain any of the videos in detail or any of the concepts in detail, I will definitely do that. The next question is quite simple. It is based on the Hammonds postulate, and it says the correct statement among the following is okay. So these are the four options. The four for the so what exactly is basically the Hammond postulate? I'll just explain in a bit. Let's just read the four statements for those of you who are aware of what exactly is the Hammond's postulate. So the first thing it says that the transition state of an endothermic reaction resembles the starting material. Okay, the transition state of an exothermic reaction resembles the product. The transition state of an endothermic reaction resembles the product. And the fourth statement is the transition state in an endothermic as well as an exothermic reaction does not bear any resemblance to either the starting material or the product. Okay, and so what exactly these are the statements, and we have to find the correct statement. So what exactly is the Hammond's postulate is basically it's part of physical it's basically like a transition state diagram where we have over here we have the reaction coordinate. Okay, over here we have the reaction coordinate or how the reaction progresses, and over here we have the potential energy or the energy. Okay, and let's say we have a reactant over here. Okay, that reactant goes there's a transition state and then we get a product. Okay, so if the product is of lower energy than the reactant, this is the transition state energy. Okay, this is the transition state over here of some energy. So if the product is of lower energy than your reactant, then we say that basically it's an exothermic reaction. Okay, this is the amount of energy that will be released because your product is more stable than the reactant, so it will be an exothermic reaction. It will be an exothermic reaction. Whereas if you talk about endothermic reaction, in the endothermic reaction your reactant is of lower energy and then your product is of higher energy. Okay, so this kind of reaction is endothermic. So basically what it states is that whichever of the two is closer to the transition state in energy terms, it will bear resemblance to that. Okay, it will bear resemblance to that. The transition state will bear resemblance to either reactant or product, whichever is closer in energy. So you can see that in an endothermic reaction, in an exothermic reaction, since the energy difference between the reactant and transition state is less, so in an exothermic reaction the transition state will bear resemblance to the reactant, whereas in an endothermic reaction the transition state will bear resemblance to a product. So if you see the two options, the third option states that the transition state of an endothermic reaction resembles the product. Okay, so this is an endothermic reaction and the transition state is closer to the product, so it resembles the product, and that is why the correct answer over here is option number 3. Okay, let's look at this question. So this is a very basic NCRT based question, and this basically is that the rate of the reaction for the following halides with sodium iodide would vary among how would it vary, like which will be the fastest, which will be the slowest. Okay, so this is basically a Finkelstein reaction. Okay, very simple NCRT based question, and over here basically your sodium bromide is formed, and because basically this iodide acts as a nucleophile and a sodium bromide is formed, and the sodium bromide precipitates out. So this is basically the driving force for this reaction. Okay, this is the driving force for the reaction, the precipitation of sodium bromide, and this is basically a SN2 type reaction. Okay, this is basically nucleophilic substitution. So in SN2 type reaction you just have to see among the three which is the most like which has a more easy approach. So you can see over here the first option has a very easy approach. Okay, over here the nucleophilic substitution can take place easily. Then we have the second option due to the presence of this isopropyl group, and third option due to this sterically hindered group of tertiary butyl this tertiary butyl, so it will be very slow. So it will be option number 1 followed by 3 and 2. So if you look at the options 1 3 2, so 1 3 2 is option number 3. Okay, and this is the last question of your 2 markers. Okay, like I said, organic spectroscopy questions I've already discussed. It's a simple question that has been asked a lot of times in your gate examination as well, and even in the next examination. So this is a ketene that is given to us. Okay, so this is a ketene, and so this is your ketene, C double bond O. Okay, and then we have been given a um, basically you can write it like this. um, So yeah, so this is the molecule that is given to us along with that, and heat is given, right? So since heat is given, it will basically be a 2 plus 2 cycloaddition reaction. Okay, 2 plus 2 cycloaddition will take place, and in this you already know that in ketenes, this carbon is the most, you can say, if we talk about electronic effect, if we go by this reaction with respect to the electronic effect, you know that this carbon over here is the most electrophilic because it is attached to an oxygen, and over here also it is attached to an sp2 hybridized carbon, right? So this carbon is the most electrophilic. And now over here, if we go by the electronic effect, like I said, we just have to find the most nucleophilic position over here. So the most nucleophilic position is because this methyl has some inductive effect. So over here the most nucleophilic position will be this, right? So this will attack over here. Okay, this will attack over here, and then this carbon over here will attack at this position. Okay, so if we draw the product, so we have phenyl, we have two phenyls basically, and we'll get a four member ring obviously. So this, to this carbon we have oxygen attached, and so this minus charge is attacked over here, and basically the methyl substitution is over here. Okay, this bond is bonded like this, so there's a methyl substitution, and then we have a your double bond. So if you look at the four options which resembles this, so this is definitely incorrect. Over here also this is also incorrect. So you can see over here they have not drawn the methyl. Okay, the methyl is missing in this position. Okay, in this option the methyl is missing, the methyl is not there. Some kind of isomerization has taken place, whereas in this case we have the methyl and the double bond present. So that is why over here the correct answer is option number 1. All right. Anyway, so I hope you found the video useful. If you did, please give it a big thumbs up. And in case you want me to make any specific video, please do request me. Or if you want me to elaborate on one particular topic, you can always comment. And even though I cannot reply, but I do read and I do read every comment, right? So anyway, thank you for watching, and I will see you in the next video really soon.